Okay, I'm going to give a quick overview of the hardware and the software infrastructure of SpiNNaker. Now, in previous workshops, this was actually very much an introduction, and in later parts of the workshop, we'd have much more in-depth information on the hardware. But we've decided for this focus workshop, we're not going to include that in-depth presentation. So this is going to be your only real view at the moment of the hardware. As I say, if you need more information, come and talk to us. If you're really not interested in the low-level parts of the hardware, you can tune out for parts of this, and I won't hold it against you. Okay, so what is SpiNNaker? I'm guessing because you're all here, you've all seen presentations about SpiNNaker. Maybe you've even used SpiNNaker in various code jams and other events. So I hope that you all have a vague idea what you think SpiNNaker is. I'll talk a little bit about that and what we think SpiNNaker is for. I'll show you SpiNNaker at the different scales and then go into details of the actual architecture of SpiNNaker, both the chip and the bigger systems, so you have some background on why it does what it does. And then I'll talk about the high-level view of how the software works on SpiNNaker. Okay, so this is one of Steve Ferber's favorite slides, I think. He loves the fact that the full SpiNNaker machine, which we're near to completing, is actually 1 million ARM cores, 1 million tiny chips all working together. But that still represents, when it's simulating a network, about 1% of a human brain. So it's still a long, long way from being able to simulate a whole brain on a machine. But however, it does represent the same amount of brain power as 10 mice. So we're quite pleased about that. We see SpiNNaker as being used by 3 kinds of people. One is obviously computational neuroscience, of which I guess you are mostly in this category. People who are trying to understand how the brain works and do neural simulations. And what you care about is accuracy of simulation, but perhaps you're less interested in real-time performance. Another category of people are also people who are into robotics, where they basically need real-time performance, but they're not necessarily interested in biological fidelity. They want to use spiking neurons to drive their robots, but if those neurons are very abstract, that's not necessarily a problem. We can cope with those too. The third type of people, of which I guess I am one, are people who are interested in learning how to understand the rules of how the brain works and to apply that to new forms of computation, to new models of how computers can work. That's a very much more abstract type of people, and I guess there aren't many people who fall into that category. This is a very stylistic overview of a section of SpiNNaker chips. Now, if you've seen the 48-node board, or even the 4-node boards in front of you, you see that there are chips and they're connected together by links. Every chip actually has 6 links. And when they connect together, they form a hexagonal grid of communication. And each of those packages, if you look on a SpiNNaker board, there's a package which contains one of our SpiNNaker chips, and sitting on top of it is actually a 1 gigabit SD-RAM. And that is used for storing all the synaptic connectivity information in spiking networks. But the actual chips connect in a hexagonal mesh, and there is actually wraparound on the edges of. Actually, there's wraparound here on the edge of systems. That there is a wraparound so that it can be used to form an entire torus. So when the chips are operating together, all they see are 6 links going out across a 2-dimensional sheet in all directions. Now, one of the main things that's particular about SpiNNaker is the way that this communication infrastructure works. So SpiNNaker does not have shared memory, for example. So one core or one chip can't see the memory of another chip. You don't have the concept like an MPI of doing big data transfers from chip to chip. All you can send are very simple messages, which are really short, from one core to another or one chip to another. And that's very much in the philosophy of a spiking neural network. If you imagine a neuron, it sends out a very simple signal, either spike or no spike, across the network, perhaps to one or many destinations. And while conventional supercomputers are actually quite inefficient at simulating those kind of systems, they're used to transferring big blocks of data reliably from one place to another. SpiNNaker is very good at sending very many messages in parallel, very short messages, spike or no spike, right across a large array. And so that is very efficient for power, and it's very well suited for neural network simulations, which is the philosophy behind the design of SpiNNaker. This is summarizing some of the things I'm saying. So we were talking about this communication and in terms of messages or packets that are being sent from one chip to another. Those packets will contain perhaps a spike information, but also the way it's designed, we can also transfer with the message a 32-bit piece of information, a data payload as it's called. So if you're writing an application needed to send a very short message, you could have 32 bits of message. in general, spiking networks don't need that, but there are some of our applications like multi-layer perceptron type networks where they do send activity values which aren't just spike or no spike, they're an activation level. So that is available in the packet. Packets are either 40-bit or 72-bit, which you may or may not care about. If you're connecting external devices, you'll care about that, but if you're just doing simulations, you won't. There are actually, there are actually 4 different types of messages we can send on SpiNNaker, and they're listed here: nearest neighbor, point-to-point, multicast, fixed route. The spikes that we send in neural simulations are multicast, and that's because they're a special type that they're sent from one place, but they can go to many destinations, like a spike in a neuron simulation can go to along many axons to many destinations. And so all of the spikes that we send are multicast packets, and they're the only type that is actually of interest to neural simulation. The rest are used mostly for system, for booting, and for gathering information at the system level, so you don't need to worry about that. There are 2 main ways of getting information on and off. As I said, one is the chip-to-chip links, that SpiNNaker has 6 links, but also every board has an Ethernet connection which you'll be using to connect to your host. And that is used both to download the information at the beginning of simulation and also to read off the results at the end of simulation. I'll say a little bit about the routing process. I'll maybe skip some of this. These slides will be available online, by the way, so if you'd like to have access to that, it's all online. And if you want to understand this process better, then come and talk to us and we can give you all the detail you need. Imagine this is a mesh of chips, and they each can be sending messages simultaneously. So the red numbers are actually their coordinates in this grid, and the little black numbers are the link numbers. As I said, there are 6 links on every chip. Now imagine that the red cores here are actually transmitting spikes to destinations. Now if you wanted to send a message from a core to one or perhaps many the destinations, these yellow ones are the destinations, how would you specify that in the message? Now, if there are multiple destinations, you could have a very long message saying, please send this message to here and here and here. But the way SpiNNaker works is to say, okay, there could be many destinations for a packet, but only one source. So what we have is a source routing system where we say every packet contains the source information, where it came from. And then when the message is transmitted, imagine this chip wants to send something to this chip. So there are neurons living on this chip that want to connect to neurons living on this chip. All it does is it launches the message saying, I am in 1.4, and there is on each chip a special device, a hardware router, which has a large table where it does a lookup of the source address of that spike. And in this case, it says, okay, this 1.4 wants to send a spike. I must use link 0, which will send it this way. And that's all it does. It sends a message this way. When it arrives here, in this link, there's a router on this table here, on this chip, which says, okay, this has got a source of 1.4, so I need to send it through this link here. And it keeps doing this, and when it reaches this chip here, this one is white because it represents a change of direction, and it says, okay, this is going to go south. And then when it arrives at the router on this chip, it says, okay, this is coming from 1.4, I know it's meant to be destined to something here, so I will send it to a core here. And that's the way the routing works. Now we have an optimization, which is if something is going in a straight line, we can say, okay, we'll not even bother putting an entry in the routing table, because if there's no entry for 1.4 in this chip, then we'll just send it out through the opposite link to where it came in. So things travel in straight lines without having to do any additional routing. It's only when they reach a point where they have to change direction that we have to give some routing resource to tell it to go down. In the second example, this chip 1.1 is broadcasting a spike, and it changes direction here. When it arrives here, it says actually it needs to go to something on this chip here, but it also needs to go here and here. So the routing table can quite easily send something to the current core on the current chip and send out copies. And it's in this way that the idea of an axon splitting and having multiple destinations is managed. So one spike can actually go to many destinations, and that's no problem at all. This can be as complicated as is required. Now all this routing is actually done by the tools. You don't have to worry about any of that. The software handles it. I'm going to talk about building up the progression from the small chips up to the bigger systems now. This is a SpiNNaker chip. It's actually a photograph of the layout of the SpiNNaker chip. I'll talk a bit about the components in a little while. That's what it looks like on your board, and if you peel off the lid, that's what it looks like underneath. As you can see, it consists of 18 cores. These are actually ARM cores. They're not very powerful cores, as I'll tell you in a minute, but as you can see, most of it is actually these little blocks, and that's actually RAM, code RAM and data RAM. So the actual cores themselves are quite small. This in the middle is the hardware router I talked about that handles all the packet flowing. And it has an SD-RAM controller which allows it to talk to the gigabit of SD-RAM that sits on top. So that's the basic chip. And if I move up a level, this is one of the 48-node boards that make up the big machine. So each of those is 48 chips and has one Ethernet adapter. At the top there are 3 FPGAs, and what actually happens is when we connect many boards together to form a larger machine, the FPGAs act as the kind of the bridges that allow the SpiNNaker links of on the edge of one board to talk to the SpiNNaker links on the next board, so that all the chip sees is a continuous hexagonal mesh of chips. They don't see the FPGAs, but they're the means of squashing all that information down into gigabit communication channels. So we put several of these boards together to form a sub-rack, and actually we can put 24 of them together to form one sub-rack, which has, I think, about 20,000 cores in that. And then we stack 5 of those sub-racks together to form one cabinet, and that's going to have about 100,000 cores, ARM cores. And then we've currently got a room in the Kilburn building where we've lined these cabinets up and we've connected them all together to form one continuous toroid. And at the moment, I think we have 5 cabinets connected together to form one continuous machine, and a 6th cabinet which is kind of wired itself to form another standalone machine, and the rest are in construction. Now, when you connect with the HBP portal, the collaboratory, I think at the moment it doesn't talk to this machine yet, does it? But very soon, when you submit a job to the HBP portal, you will actually be running on our 700 board, well, currently 500 board connection. So that's 700,000 ARM cores all working together. Okay. Yeah. So that's kind of really what I've just said. So we have a 5 cabinet machine, which is, it's kind of online and available. That's, yeah. And anybody, whether they're connected with HPP or not, can in principle get permission to run jobs on there. They're kind of restricted at the moment to being running standard Pine scripts, but I think we may be able to change to provide more customization soon. The other thing we're working on is, as part of the Human Brain Project, we're actually developing SpiNNaker 2. So just when you thought SpiNNaker was all you needed for your simulation needs, we're doing SpiNNaker 2, which is in collaboration with our colleagues in TU Dresden, who are doing a lot of the back-end stuff, and that is about 10 times as much capacity as the current chip, so that one of these 48-node boards will actually be fitting onto a single chip, and that's quite exciting. So we're expecting to have those chips in about 3 or 4 years, so we have several steps to go through, but by the end of Human Brain Project, we expect to have the equivalent of these boards, but with many SpiNNaker 2 chips, and then you'll be able to simulate 10 times as many neurons, or perhaps the same number of neurons with more detail. Anyway, if you want information on that, come and talk to me. Right. Hopefully, I haven't lost you so far. I'll talk a little bit. This is the only really detailed part of the talk, which if you're not really a hardware person, is perhaps a bit less interesting. But so the SpiNNaker chip consists of 18 cores, and the way we view the cores are that they form a kind of a parallel set which is connected to the hardware router on the one hand, which connects to the 6 links, but also behind it there are some system resources. So there is a system bus which connects it to the SD-RAM controller and to other peripherals over the Ethernet interface. These are completely general purpose cores, which are ARM 968s. They run at 200 megahertz, which is not fast. You know, this is not an Intel i5 we're talking about here. There is, as I mentioned, no floating point. So if you're trying to write something and say, okay, where's floating point? We can run the floating point library, emulating floating point, but you know, the performance is not great on floating point. But we do assume that a lot of the neuron simulation will be done with fixed point arithmetic, and that's relatively fast. There was also no memory management. If you're used to running like virtual threads and all the process stuff of your favorite operating system, we don't have that on SpiNNaker. It's a very bare metal machine. It's geared for low power and neural simulation, and it's not great on booting Linux, for example. I mentioned the memories. There is a every core has a 32 kilobytes of local memory, so the neuron models are actually quite constrained in how complicated they can be. But each core also has 64 kilobytes of local data space called DTCM. That's instruction tightly coupled memory and data tightly coupled memory. It means that the memory is very strongly integrated with the cores. It's not across a bus from the core, technical jargon. And those local memories are only visible to the local core, so one core can't access the memory of another processor, which if you're trying to write your own application can be a little bit hairy. What you can do, though, is they can all see the shared 1 gigabit of shared address space, 128 megabytes, so that they can actually exchange data by writing to the common store and then reading back out again. So there is some communication. And the other thing I mentioned was there's a router, which is the thing which directs the flow of traffic around the machine. I mentioned at the top that there are 18 cores. When the machine boots at the beginning, when you first plug it in, all the cores are identical. They're treated exactly the same, and they each go through their own little boot process to get ready to run simulations. The first one, which completes that process, says, okay, I wish to be in charge, because we're trying to build a system which is highly redundant, and so to have one core which is always the guy in charge means that if that core was broken or didn't manufacture properly, the whole chip would be dead. So as part of our experiment into redundant parallel computer systems, we have this boot process which allows any of the 18 cores to be the guy in charge, called the monitor processor. And so the first one, which completes the boot process, says, I'm the monitor processor, and all the rest of you guys are just running applications. So that's the way the boot process works. And in principle, we guarantee 16 of the other cores will be available for applications. And then that leaves one free just in case we have a manufacturing defect, but there's one spare core. Okay, that's all I'm going to say about the hardware. Quick overview of the software. So in essence, there's two stacks going on in the software. On the left, we have the stuff running on your host machines. So that could be your laptop, or it could be one of our host machines if you're accessing the portal. And the pink stuff there is all running in Python code. In essence, so what is happening is you're writing your script in the Pine language, and you feed it into our tools. Now, we have a front end for a number of different languages, I guess. Pine is the one we've mostly done, but we also have a more generic input language called the graph front end, which allows you to specify any problem as a graph, where the vertices of the graph are the computation, and the edges of the graph represent the communication between those vertices. But Pine is the main front end, and what it does is it translates and interprets your neural network specification and passes it into a mapping process. Now, what that process has to do is decide for each group of neurons, which core in the machine should I put this group of neurons on, and how do I connect all these cores together with those routing tables to make sure that when you spike on this core, the spikes end up at all the cores they're meant to go to. That's the mapping process. I'll talk a little bit about that in a few minutes. And then we have an interface which takes all those files that have been generated and then pumps them down the Ethernet connection to the SpiNNaker side. So this line represents the boundary between the host machine and the SpiNNaker machine. Now, everything on the SpiNNaker side is green. This represents C code. We primarily program all the executables running on SpiNNaker in C. I think we have got some forays into C++, but that's kind of very much at the fringes, I think, of what we do. So when you run a simulation, it generates the files it needs to generate, and then they get sent across here to the SpiNNaker board. Now, we have effectively 3 levels of software on SpiNNaker. One is a very low-level system management called SARC, which runs as soon as the chip is booted. That's the system real-time kernel, I think it's called, is it SARC? Yeah, we call it SARC. It's literally the thing which has the lowest level control of all the resources, like the SD-RAM control. It sets up the system. Now, on top of that, we have a layer of software called the event-driven API. Now, if you're writing a new application, you don't necessarily have to have this. It provides infrastructure for event-driven applications, and spiking neural networks are an event-driven application. So we always use it for spiking neurons, but you don't need it if you're writing a new application. And then sitting on top of that is the actual application code. Now, if a core is running some neurons, it'll be an executable dedicated to running LIF or exponential or whatever the neuron type is. But we have other executables that also run. Some cores are responsible for gathering information. We have packet gatherers that take messages and convert them into formats that can be sent back to the host. We have what do the other executables do? I'm trying to think what the other ones do. Other cores, what are they doing? There's packet gathering, there's the neuron models, re-injector, that's the other one I was thinking. Yeah. So that'll do, yes. Okay, so every core is given an executable to run and some data to run. So if you're running a neuron model on one core, you would not only need the executable, but you'd also need the information about what the synapses were, what the neuron parameters were, and that all has to be passed to that application. I'll probably come to that in a minute. Okay, I'll come back in a moment. Just to let you know that the mapping process, this is what the tools are doing when you run the SpiNNaker tools. I mentioned there's a front end which follows at the mapping. Now the mapping has got basically 4 main tasks. Partitioning is, imagine you've created a group of 10,000 neurons in your Pine script, and you want them to be run on the cores. Now one core can't do 10,000 neurons, so we have to basically take your group of neurons and break them up into chunks, and each chunk can be given to one processor core to simulate. So that's called partitioning. Placement is where we say, okay, we have these chunks of neurons. I'm going to take this chunk of neurons and place it on this core, and I'm going to take this chunk of neurons and I'm going to place it on this core. And it tries to do the placement so that the paths of communication between these cores are minimal, because obviously we want to reduce the traffic flow as much as possible. Then it does the routing, which is saying, okay, this core here is sending lots of spikes to this core here. So we'll make a path that takes this spike along here, perhaps avoiding a hotspot here to this core here. So there's a lot of decisions about what the flow of traffic should be on the machine, and that's called routing. And at the end of that, it generates these tables I mentioned that are loaded down to the cores to say how to do all the turns as the traffic is flowing. The last step is data generation, which is, okay, a group of neurons is going to go on a core, but it needs neuron parameters, it needs synaptic data, and the whole process of building those files ready for download is called data generation. And we have to do that for every core in the simulation. And then at the bottom, then it goes to a thing called SpiNNaker, which is the tool that actually then takes that data and loads it onto the machine. Okay. Just so, again, this is just for background really, what's actually being loaded on here. So every core, and there are 16 per chip, needs a C executable, which is about 32 kilobytes, some local data for its data local memory, that could be neuron parameters, and some what I call the application shared data, which goes to the shared SD-RAM. And that's usually synaptic data, which is by far the biggest data chunk that every core needs. And that can be up to 8 megabytes. If every core used its maximum allowance, that would be 8 megabytes of data. And then at the chip level, we need to load a routing table to every chip, and there are occasionally other shared data tables that you need to worry about, which we also load. Okay, so all that has to be loaded at the beginning of simulation, and we have found that for big networks, that load time can be quite considerable for big networks, but we are working on that. Yeah. Just want to give you, to finish off, a brief view of what's happening on the chip during all this. So when you run the tools, it compiles a network description, it does that mapping process, it generates all those data files, and then it loads those files. So that's all being done by the host. Then, before simulation can start, because if you think about it, we're loading all these files one at a time. Some chips will have their files very, very quickly. Others have to wait until near the end. They're going in one at a time. So we have to wait until every core on the machine has got its data, and then we do this thing called synchronization, where we say, okay, is everybody ready? And everybody goes back and goes, yes, we're ready. Or maybe not. But when everybody's ready, then we say go, and we trigger the simulation across the whole machine at the same time. Then all the cores hopefully work together to complete the simulation, because they're all running on their own clocks, so that there isn't, other than this synchronization, there isn't much step-by-step synchronization across the machine. So the synchronization calls everything to start at the same time, and then hopefully if you said run for, I don't know, 10,000 milliseconds, it waits that length of time, and then hopefully all the cores say, yes, I've completed. There is a polling going on from the host to say, have you finished yet? And when everybody says they've finished, controllers hand it back to the host, which then pulls back all of your data. Now, we do actually have the capability to do pause and resume now, where basically we run for a bit, generate lots of data, everybody pauses and we take all that data off to clear all the buffers out, and then we resume the simulation, so we can break it down into chunks, which is, I guess we've had that for more than a year now, haven't we? It's quite an old functionality, yeah. But I tend to think of it as you run the simulation, everything stops, then you read back all the results for visualization. And that's it. I mean, there's going to be a lot more detail, particularly on the software side, over the next couple of days. But hopefully this has given you a bit of a feel for what SpiNNaker is and how it does it. Feel free to ask me about any in-depth technical questions you have. Oh yeah, just one more thing, yes. This is a quick advert. We do actually sell the larger SpiNNaker boards. They're about £7,500, which, you know, I wouldn't advise you to buy one for home use, but by all means, if you want one for institution, the only restriction is that we're not allowed to sell them for commercial purposes, so you couldn't use it to do a startup or something. But if you're doing academic research, even if you're in a company, as long as it's academic research, we can sell them to you. So feel free to come and talk to me if you're interested. We do, as I say, loan out the 4-node boards. We have a limited supply, so please talk to me or Christian or Andrew before taking them away. But we do loan those out for people to play with. Okay, and I think that's the end. Thank you very much.